Hello everyone, welcome to this lesson precursor for next weekend's lesson. So this is a short video to introduce you to some of the concepts that we'll develop more fully in the classroom. So try to put aside any distractions and focus, because there are going to be questions posed today that I'll ask you to answer in the class. Okay, so we are looking at classifying numbers, and I've got a number tree here, and I'm going to start at the bottom of the number tree with counting numbers. So counting numbers is one of the first things you learn as a child, obviously after you've learned to speak, but you do little rhymes like 1, 2, 3, 4, 5, something to do with fishing, and then buckling shoes and things like that. Actually, for most people, the concept of zero, that doesn't come as quickly as counting things. The concept of zero as an absence of something, sure, there aren't any apples. But the concept of zero as a number takes a little bit longer to establish. I'll give you a little story to kind of try and illustrate that. There's a story about this famous French existentialist, Jean-Paul Sartre. He goes into a coffee shop and the waitress asks him, "What would you like?" And he says, "Can I have a coffee, no cream?" So the waitress walks away. A little while later she comes back and she says, "I'm sorry, sir, but we're out of cream today. Can I give you a coffee with no milk instead?" So, okay, that's to try and illustrate the difference. Actually, the concept of zero as a number, that wasn't fully accepted, especially in Europe, until about the 16th or 17th century. So, understanding that zero is a number takes a little bit more time. Okay, so if I combine together zero and the counting numbers, those two together, I'm going to call them natural numbers. And the opposite of natural numbers is negative integers. So negative numbers, negative whole numbers. And again, that concept took longer for people to understand and establish. So for instance, if you'd said to a Roman, "What is 5 take away 7?" they would have said, "Well, you can't do it. You can't take away 7 from 5. And you say, "Well, sure you can." And they'd say, no. If you have 5 apples and I try and take away 7, how's that going to work? And in that sense, they're right. Nowadays, you might say, "Oh, I've got £5 in my bank account, but I've just spent £7 on my card, so I'm going to be overdrawn by £2. And so the concept of negative numbers is quite easy for us to understand nowadays. But it did take a little bit longer. Actually, I say it's quite easy for us to understand. There was quite a famous example of a lottery scandal, which is some sort of scratch card that Camelot introduced. And on the scratch card, you scratched off the central panel, and that gave you a temperature. Okay? And there'd always be cold temperatures. So there'd be like -8 would be in the centre of the scratch card. And then you had to scratch off some other squares and hopefully reveal a temperature that was lower than that -8. And if you got a temperature that was lower than -8, you won a prize. So people would scratch it off and they'd say, "Well, I got -5. That is lower than -8. And they would go into the shop and they would say to the shopkeeper, "Look, I've won some money. Can I have some money?" And the shopkeeper would say, "Yes, you're right. -5 is lower than -8. Here, I'll just put it in the machine and see how much you've won." And the machine would say, "No, you haven't won anything." And so they would write to Camelot and say, "Your game is rubbish. -5 is less than -8. Why didn't you give me the prize?" And in the end, Camelot had to just withdraw it because so many people were complaining because they didn't understand that lower than -8 is -9 and -10. So you can see negative numbers, even today, cause some confusion. Okay, so we've got some empty boxes here. There's an empty box here. Oh, let's just get rid of that. There's an empty box here. And I'm going to ask you in the class, what rational numbers are not integers? What's the group of rational numbers that aren't integers? And then I'm going to ask you in the class, what's the group of real numbers that aren't rational numbers? And I'm going to ask you in the class, okay, what numbers are not real numbers? So that's stuff that you need to think about and you'll be asked about in the lesson. But actually right now we're going to go down here and we're going to ask ourselves what categories can we split counting numbers into? And we're going to split them into two categories. The first one is prime numbers. So some counting numbers are prime numbers. And our second category is going to be numbers that aren't prime numbers are composite numbers. So composite. Okay, so we've broken counting numbers down into prime numbers and composite numbers. Okay, so what is a prime number? Well, I'm going to tell you that 2 is the first prime number. So 2 is the very first prime number. And 2 only has 2 factors. So if you want the factors of 2, there'd be 1 and 2. So that's a prime number because it only has 2 factors. 3 is a prime number because its factors are 1 and 3. It only has 2 factors. 4 is not a prime number because its factors are 1 and 4, but it's got another pair of factors which is 2 and 2. So 1, 2 and 4 are its factors. So that's not a prime number. 5 is a prime number. 6 isn't a prime number because it's got 1, 2, 3 and 6 as factors. 7 is a prime number. 8 isn't a prime number. In fact, 2 is the only even prime number. So when we're talking about prime numbers, there's only one even prime number. Any other even number is not going to be a prime number. I mean, that sounds strange, but then 3 is the only multiple of 3 that's a prime number. So you can see that it follows through, the pattern follows through. All other multiples of 5 other than 5 are not prime numbers. Okay, now I'm not going to carry on up to 100, but you get the idea. We can look at a number, say we can look at the number 43, and we can ask ourselves, is that a prime number? Well, 1 and 43 are factors of it, but are there any other factors of it? So for instance, does 2 go into it? Well, it's not an even number, so 2 doesn't go into it. Does 3 go into it? No, it's not a multiple of 3. Does 5 go into it? Okay, I didn't check 4. You only need to check prime numbers to see if they're factors. You don't need to check composite numbers. So I check to see if 2 is a factor, then I'll check to see if 3 is a factor, then I'll check to see if 5 is a factor, then I'll check to see if 7 is a factor, and none of them are factors. And I think I think I'm done now. I don't want to go any higher than that because 7 sevens are 49, which is greater than 43. So if you're going to get a prime number that's more than 7 as a factor, then the other number would have to be less than 7 because, 7 sevens are 49. So if you're going to do, 11 times something and it's going to give you 43, well, it would have to be an 11 times quite a small number. 11 times 4, for instance, but that will give you 44. Okay. How can you check if a number is prime? For instance, is 119 a prime number? Okay. So let's see if it's divisible by 2. For numbers that are divisible by 2, even numbers end in one of those digits, so it's not divisible by 2. To check to see if it's divisible by 3, you just add up the digits. So 1 plus 1 plus 9 is 11. And 11 isn't a multiple of 3, so 119 isn't a multiple of 3. Is it divisible by 5? The units digit would have to be 0 or 5, and you can see it's not divisible by 5. Okay, what about the rule for divisibility by 7? Okay, so for divisibility by 7, what I'm going to do is, the number is 119. I'm going to remove the units digit, which is this one, 9. I'm going to double it, 18, and I'm going to subtract it from 11. So 11 subtract 18, which will give me minus 7. Now, minus 7 is a multiple of 7. It's a negative multiple of 7, but that doesn't matter. Yeah. So it is a multiple of 7. And so 119 is divisible by 7. So this is not prime. This is composite. We know 7 is a factor of that. Is 127 a prime number? Well, it's not even, I can see that straight away. If you add up the digits, you get 10, so it's not a multiple of 3. It's not a multiple of 5. Let's try the rule for divisibility by 7. So that's going to be 12 minus double 7. Double 7 is 14, which will give you minus 2. Minus 2 is not a multiple of 7. So no, 127 doesn't have 7 as a factor. 11, the rule for divisibility by 11 is you alternate the sign of each of these digits. So 1, positive, subtract 2, plus 7, like that. So that becomes positive, that becomes negative, that becomes positive, and so on if you had more digits. And so 1 subtract 2 is minus 1, plus 7 is 6. And 6 isn't divisible by 11, so 11 is not a factor. And I think I'm done there. I don't think I need to test 13. For 13, you would do 4 times the units digit, so 28, and add it on to 12. But I don't think I need to do that because 13 times 13 is 169, and that's way too big, so I'm not really looking for that. Okay, so I'm pretty sure that this one is a prime number. So this is prime. Yes, this is prime. Okay, now we've gone large. We've gone huge. Is 4,294,967,297 a prime number? And the reason I asked this specific number is it's a famous number. There's a set of numbers called Fermi primes. And Fermi primes are found by using this equation, 2 to the power 2 to the power n plus 1. And Pierre de Fermi said, he's a famous mathematician, he said, if I put in 5 into here, so this would be, according to him, the 5th Fermi prime number, and you stick that in the calculator. So I stick that in the calculator, so let's turn the calculator on. 2 to the power, let's do brackets, and then 2 to the power 5, and then let's just add 1 to that. Oops, not add 1, I need to go down here, add 1. So that there's that same number, okay? And is it a prime number? Well, I don't fancy checking it. I don't fancy doing all the divisibility rules. I'd have to do so many of them to do it, to check it. And it would be a long process. It would take me age. In fact, Pierre de Fermi said, this is a prime number. I have checked it by clever methods, and I'm certain that this is a prime number. And it turned out not to be a prime number. I think 641 is a factor of it. Let's try dividing it by 641. Yep, there you go. You get whole number as an answer. So 641 is a factor of that. So it's not a prime number. So what you realise is actually checking a number is prime. And if it isn't prime, finding its factors is actually quite a long-winded and difficult process. And prime numbers themselves are important numbers because you can multiply together 2 prime numbers and get a huge number, and that only has one way of being broken down into the 2 original prime numbers. But if once you've done it and you've multiplied together 641 by 6700417, and you've got that number, God help anyone who has to then try and decompose that number. Actually, there is kind of a clever way of doing it, but only for that number, because we know it's one of the ones that's formed by this equation. So, okay, so prime numbers are going to be important in mathematics. They're going to be important they're important in all forms of internet security. So internet security is based on this idea that if I take 2 large prime numbers, I multiply them together to get a huge prime number, and then only people who know the 2 original prime numbers can access my website, then if you're somebody who doesn't know it and you've got that huge prime number and you need to break that huge prime number down, it's going to take a computer a long time to find out, so that a huge composite number, and you need to break it down into its 2 primes. It's going to take a computer a long time to do that. And that's how most internet securities work. You take very, very large prime numbers, you multiply them together, and then you say, right, now figure out what prime numbers I use to make that composite. Okay, so now we're going to basic indices, and here I've got 4 times 4 is 16, and I'm going to write it as 4 with a little 2 on the top. That's called a superscript 2, but we would pronounce that as 4 squared. So 4 squared means 4 times 4. So 4 squared, that means 4 times 4. And 4 times 4 times 4, so 3 4s being multiplied together, we'd call that 4 to the power 3. 4 cubed, we would say. And 4 times 4 times 4 times 4 times 4, we would call that 4 to the power 5, because there's 1, 2, 3, 4, 5 of them all being multiplied together. Now, if I ask you what is 4 squared times 4 cubed, you can probably tell me the answer straight away. 4 to the power what? I'm not asking you for the numerical answer. I'm just asking for the, in the form of indices, what is that answer? And if you're not sure, we can go back to what they mean originally. 4 squared means 4 times 4. And I want to multiply that by 4 cubed. And 4 cubed means 4 times 4 times 4. And so really I'm doing 4 times 4 times 4 times 4 times 4. It would be 4 to the 5. It would be the same as this one here. So 4 squared times 4 cubed equals 4 to the power 5. Okay, I just kind of added those powers effectively. Okay, so 5 cubed means 5 times 5 times 5. I know you can answer this, but I'll ask you that in the lesson. I know you can answer this, but I'll ask you that in the lesson. So when I ask you that in the lesson, you put your hand up and say, I can definitely answer that. Write 81 as the product of its prime factors. Okay, so I'm going to decompose 81 into prime factors, and I'm going to do it in a particular way, and this is exactly the way that I want you to do it when you get to do the homework on it. The homework on it I'll set in the lesson at the weekend, and then I want you to do it this way. In school you're taught a different way using spider diagrams. We're not going to do that. It's not a good way for reasons that will become apparent later on. Okay, so I want to try and divide it. So I'm doing 81 and I'm dividing it like you would do this division, and you know, maybe you'd divide it by 3 or something like that. But I'm doing the division downwards instead of upwards. It really doesn't make any difference. It shouldn't cause you any problems. Okay, now I'm going to try dividing it, but I'm only going to try dividing it by prime numbers, like we did earlier on when we were trying to check if numbers were prime or not. So 81, I can see that 2 doesn't go into it, and I can also see that 3 does go into it. So I'm going to divide it by 3. So I'm going to divide it by 3. And I know that that's going to give me 8. 3's into 8 go 2 times. So 2 times. And then that gives me the remainder of 2, which I'll put at the top here. And 21 is 7. So that gives me 27. And then now I'm going to do another division. I'm going to say, can I divide it again? And I can see that 2 doesn't go into it, but I can see that 3 does go into it again. So I'm going to divide it by 3 again. And then, well, I know that that's 3 times 9. So I'm going to call that 9. And I'm going to do a division again. And I know that 3 goes into that. And I know that 3 goes into that 3 times. Now I've got a prime number here at the bottom. So I stop. Once my bottom number is a prime number, let's just change that to being blue again. Once my bottom number is a prime number, then I stop. And then I'm going to multiply together all these numbers. I'm going to multiply together this one and this one and this one and this one. And I'm going to say that they equal 81. So I'm going to say 81 is 3 times 3 times 3 times 3. So 81 is 3 to the power 4. Okay? You probably knew that already. So it's not a tricky one. 1, 2, 8, I'm going to do exactly the same thing. I'm going to do 1, 2, 8. It's easy. 2 goes into it. I can see that 2 goes into it 64 times. I'm going to divide it again. I can see 2 goes into it again. And 2 goes into it 32 times. I'm going to divide it again. 2 goes into it still. And then that's going to be 16. I'm going to divide it again. 2 again is a factor. And that's going to be 8. Whoops, I wanted blue. 8. And I'm going to divide again. 2 still goes into it. and then that's going to be 4, and I'm going to divide it again. Still 2 is the factor. Whoops, wrong colour. 2 is the factor. And that gives me 2, which is a prime number, so I stop, and then I just multiply together all of these numbers to get 1, 2a. All of these outside numbers, all the numbers on the outside. And so that gives me 1, 2a is 2 times 2 times 2 times 2 times 2 times 2 times 2. There's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 2 to the power 7 is 1, 2a. Okay, 2 easy ones to do. They were not hard at all. One of them had just 3 as a factor. The other had just 2 as the factor. Okay, so this is a big number, but we've got it by multiplying together the two numbers. This 10,368 is the multiplication of 128, which we just did here, and 81, which we just did here. So they're saying write that as the product of its primes. And I can already break 128 into its prime factors. I already know that's 2 to the 7. That was the example I just did here. It was 2 to the 7. And I can already do 81. That was 3 to the power 4. That was 3 to the power. We did that here. It was 3 to the power 4. Okay. So if you multiply them together, they're going to give you 10,368. So there we go. We've done it. 10,368 is 2 to the power 7 times 3 to the power 4. Those are the prime factors of 10,368. That 46,200, that's not, this was two numbers that we multiplied together. This is not two numbers that we've multiplied. Well, I mean, it is two numbers multiplied together. I mean, I could quite easily say 46,200 is equal to 462 times 100. That's obvious. 462 times 100 will give you 46208. And then what I'm going to do is I'm going to break each of these down into its prime factors. So I'm going to start with this one, 462, 462, and I'm going to divide it. I'm going to see, well, 2 is obviously a factor, so I'll start off by dividing it by 2. And that's going to give me 231. And then I'm going to try and divide 231. And I can see that the sum of the digits, 2 plus 3 plus 1 is 6. So that immediately tells me that 3 is a factor. So 3 is a factor. So 3 is a factor. So 3's go into 23. Well, they go into 21 7 times, and that leaves me a remainder of 2, and then 3 goes into 21 7 times. So that's 77. And 77, I kind of know that. That's my 7 times table or my 11 times table. So I'm going to divide it by 7, and then that's going to give me 11. And 11's a prime number, so I can stop. So 462 is, let's just highlight those. It's those numbers multiplied together. So 462 is 2 times 3 times 7 times 11. Okay. I need to do the 100 as well. I need to do the factors of the 100. So I'll do the same thing with 100. 2 goes into it, 50. 2 goes into it, 25. 2 goes into it, 5 and 5. Okay, so these are the prime numbers, and then therefore that's my prime factorisation of 100. So 100 is actually 2 squared times 5 squared. Okay. Now I was multiplying these two numbers together to get 46,200. So that means if I multiply these two numbers together, I'll get 46,200. And here I've got a 2, and I'm multiplying it by a 2 squared. And a 2 squared I know is a 2 times 2. So effectively I've got a 2 times a 2 times a 2. So that will be 2 cubed. So I'm going to rewrite that as 2 cubed. So I'm going to rewrite that as 2 to the power 3 times, I've got a 3 here. I don't have any 3's here. So I'll just write a times 3. I've got a 7 here. I don't have any 7's here. So I'm going to write times 7. I've got 5 squared here. I don't have any 5's here. So times 5 squared and then times 11. So because we knew two smaller numbers that multiplied together to give us that made it much quicker for us to break it down into its prime factors. Otherwise, it would have been a longer process for us to do. Okay. So this is an exam style question, and it's sort of similar to the last question. I'm going to leave that. So maybe write it down, have a go at it, and then I'm going to ask you in the class if you're able to do that and if you're able to find out these numbers x, y, and z. That's a type of question you might get in exams. So we've already, in this lesson, moved forward to the idea of numbers that you might get in the exam. Okay, I want to talk about highest common factor, HCF, and lowest common multiple. And I want to start off with the concept of a factor. So, and this is related to prime numbers. So 12. What are the factors of 12? Well, 1 times 12 gives me 12, and 2 times 6 gives me 12, and 3 times 4 gives me 12. So those are all of the factors of 12. Okay, so numbers that go into 12, whole numbers that go into 12. And I'm going to say, well, what is a multiple? Well, multiples of 12 are, well, 12, 24, 36, 48. Just, you keep multiplying it. You keep doing 12 times 1, 12 times 2, 12 times 3, 12 times 4. Okay, so now I've got two numbers here, and I'm asking you, what is the highest common factor? And so the highest common factor is the number that goes into both of them, the factor that works for both of them. And obviously, 1 is a factor of both of them. So the lowest common factor would be 1. I'm not after that. I'm after the highest common factor. So what I'm going to do is I'm going to look at the smaller number. I'm going to focus on the smaller number and I'm going to look at its factors. 6 has got factors of 1 and 6. I'm going to ignore the 1. It's the 6 that I'm more interested in. Is the 6 a factor of 10? Well, no, it's not really. Okay, I'm going to look at the other factors of 6, 2 and 3. And I'm going to look at the bigger one because I'm after the highest number. 2 and 3. But 3 isn't a factor of 10. So that's not a common factor. The other factor was 2, which isn't the biggest one, but you know, the biggest one didn't work, so what do I do? 2 is a factor of 6 and it is a factor of 10. So the highest common factor here would be 2. The highest common factor would be 2. Okay, what's the lowest common multiple? So this time I'm going to focus in on the larger number. And I'm going to do multiples of 10. So first multiple of 10 is 10, but 10 isn't a multiple of 6. So it's not a common multiple. Okay, 20, that's the next multiple of 10. No, that's not a multiple of 6. 30, yes, that is a multiple of 6. So the lowest common multiple would be 30. That's a multiple of 6 and a multiple of 10. Highest common factor of 8 and 12, do the same thing. Factors of 8. Factors of 8, the smaller number, are 1 and 8. 8 doesn't go into 12. Okay, all right, let's do some other factors of 8. 8 are 2 and 4. 4 goes into both of them. So 4 is the answer that I'm looking for, the highest common factor. And then here again, I'm doing the multiples. And when I'm doing the multiples, I look at the bigger one. Look at 12. Multiples of 12. 12. No, but 8 doesn't go into that. Okay. Right. Next multiple of 12. 24. Yeah, 8 goes into that. Okay. So 24. So 24 is the answer that I'm after there. Okay. The numbers have gotten quite big now. So 90 and 42. I'm going to look at the smaller number again. And I'm going to say, what are the factors of 42? Well, 42 times 1, and I'm looking for the bigger one. So 42, that's not a factor of 90. Okay, let's look at the next factors. 21 times 2. 21 is not a factor of 90. So, okay, let's look at the next ones. Next ones I can think of are 6 times 7, and 6 is a factor of 90. So I think it's 6, but the numbers are getting bigger, so it's a bit harder for me now. Okay, here I'm going to go to the bigger one of the two. So 90 is the bigger one of the two. And I'm going to do multiples of 90. So I'm going to do 90, nope, that's not a multiple of 42. 2 times 90 would be 180. Nope, that's not a multiple of 42. 3 times 90 would be 270. No, that's not a multiple of 42. 4 times 90 would be 360. No, that's not a multiple of 42. 4 times 90. I'm getting to quite big numbers now. So I'm sort of finding it a little bit difficult. So I'm going to skip this. I'm going to skip this one as well. And I'm going to go to the algebra. And I'm going to go to the algebra here. And this is going to help me to do these. And I'm going to show you how the algebra is going to help me to do these. Okay, so if I look at this one here, I'm looking, in this column, I'm looking for the highest common factor. So these are my two numbers. The first one is a squared b cubed c, and this one is b times c squared. So I'm looking for things that are common. And I can see that there's an a squared in this one, but there's no a squared in this one, so it's not common. I can see that there's a b cubed in this one, but in this one there's just a b, not a b cubed. So the b is common, but the b cubed isn't common. So I'm going to say that the b is common, but not the b cubed is common. And here I'm going to say the c is common. There's a c in this one, but there's a c squared in this one. So the c is common, but the c squared isn't common. So I'm going to say the c is common. And so I'm going to say the common factor of this is bc. The common factor of this is bc. B and c. There's a b in both of them. There isn't a b cubed in both of them. And there's a c in both of them. There isn't a c squared in both of them. There's a c in both of them. The c squared contains a c. The c squared is really a c and then another c. Okay. Now we'll do this one. Oops, let's do it in yellow first of all. So these are my two numbers. What is common? Okay, so the d isn't common. The e is common, but the e squared isn't common. The f is common. There's two f's here. There's three f's here. So two f's are common, but three f's aren't common. This has got two f's in it, but it's got a third one in it. The e was common. The d, they're sort of written in the wrong order here, aren't they? So there's a d squared here and a d here. So the d is common. And there's a g here, but there isn't a g in this one. And there's a j in this one, but there isn't a j in the first one. So, okay. So my common things are, I've got a d in both of them. I've got an e in both of them. And I've got an f squared in both of them. So let's go back to 90 and 42 and see how that helps us. So let's go back to 90 and 42. So we had our numbers, which were 90 and 42. And what we're going to do is we're going to do the prime factorizations of 90 and 42. So 90, 2 goes into that. It's going to be 45. And 5 goes into that. So it's going to be 9, and 3 goes into that, and 3 goes into that. So 90, its prime factorization is 2 times 3 squared times 5. 2 times 3 squared times 5. Okay. Let's do the next one. Let's do 42. 42, 2 goes into that, 21, 3 goes into that, and 7. So 42 is 2 times 3 times 7. And then now look at what's common. And now that let's look at what's common. Whoops, I'm trying to rub it out. Okay. Now let's look at what's common. So there's a 2 in both of them. There's a 3, but not a 3 squared. The 3 squared isn't common, but the 3 is common. And that's it. So 2 and 3 are the common factors. So the common factors are 2 and 3. And so 6 is the lowest common multiple. I already figured that out. Okay, let's go here to, the highest common factor. Let's go to lowest common multiple. Let's go to lowest common multiple. When we want to do the lowest common multiple of these two, what we want to do is we want to include everything, but not repeat things unnecessarily. So what we want to do is multiply everything together, but extract any repeats. So let's see. We're going to use an a squared because there is an a squared here and we want to use everything. There isn't an a squared in this one, so we don't have to worry about it being repeated. There's a b cubed in this one and there's a b in this one. So I'm going to use the b cubed, but then I won't use this extra b because then that would be a repeat. The b cubed already has b's in it, so I don't want to repeat it. And then I'm going to use the c squared from this one. I'm going to use, so that will give me everything, but it won't unnecessarily repeat anything. So I'm going to say that I want a squared times b cubed times c squared. And that's going to be my lowest common multiple. So my lowest common multiple of these two, again, is going to be that same idea. I want to repeat everything. I don't want to repeat everything. I want to include everything. So I'm going to include this 2, but I'm not going to repeat it. So let's just move that out of the way. I don't actually need, let's move all of those out of the way. I'm going to include the 2. I'm going to include the 3 squared. I won't include the 3 because the 3 squared already has a 3 in it. I'll include the 5 and I'll include the 7. So I'm not repeating it. I'm not repeating the 2. I've already got a 2 there. I'm not repeating the 3, but I'm not missing anything out. So it's 2 times 3 squared times 5 times 7 times 7. Okay, so what have we got? Well, 2 times 5 is 10. And 3 squared times 7 is 9 times 7. And 9 times 7 would be 63. So 630 was my answer. 630 was my answer. I couldn't find it when I was just trying to do multiples of 90. I think I gave up a little bit easily, to be honest. But I was easily able to find it once I was doing that. Okay, so let's do the same thing here for the 420 and the 175. So let's do the 420 and the 175. Actually, you know what? Rather than make it longer, I will leave that 420 and 175 and we'll try and do it in the lesson. Okay, so this is more like an exam style question. My children are all in full-time school. That means they're aged between 5 and 18. Fascinatingly, the product of their ages is 60,000 and 60. Do you know for sure how many kids I have? And do you know for sure what their ages are? So again, we're thinking about the prime factorisation of this number. And we're thinking about how can we do that prime factorisation easily? How can we easily do that prime factorisation? So maybe think about splitting it into 2 numbers first, 2 multiples first, whatever multiples you want to, and then do the prime factorisation. I mean, you could just do the prime factorisation without splitting it. It would still work. It just might be a bit slower process. I'm leaving that, again, something we'll do in the lesson. What do you imagine happens to the gaps between prime numbers as we get to larger and larger numbers? So I'm going to start off We didn't do them, but we suggested doing the prime numbers from 1 to 100 before. And then after that, we looked at 119 and we said, yeah, that was a prime number. And then we looked at 119 wasn't a prime number, it was a composite number. And then we looked at 127 and we said, that is a prime number. So I'm just wondering, like, you know, what happens to the gaps between prime numbers? So I'm going to start with something like, I don't know, 110. 110, is that a prime number? No, because it's even. Okay, then I'm going to go to 111. Is that a prime number? Well, the digits add up to 3, so I know that's a multiple of 3. 112, is that a prime number? No, it's even. 113, is that a prime number? 113, well, that does look like a prime number to me, because 2 isn't a factor, 3 isn't a factor, 5 isn't a factor, 7 isn't a factor, 11 subtract 6 will give me 5, which wouldn't be a multiple of 7, so 7 isn't a factor. And then 11 isn't a factor, so I don't think I need to go any further than that. So 113 is prime. And then 114 is even, so that's not going to be prime. 115 is not going to be prime. 116 is even, so that's not going to be prime. 117, that's going to be, the digits add up to 9, so that's going to be a multiple of 3, so that's not going to be prime. 118 isn't going to be prime. 119, that was the one that we did in earlier on. We said 7 was a factor of that. 120 isn't going to be prime because that's even. 121, you probably recognize that. It's 11 squared. That's not going to be prime. 122, that's not going to be prime. 123, add up the digits. They add up to 6. That's not going to be prime. 124, that's not going to be prime. 125, that's not going to be prime. 126, that's not going to be prime. 127, the digits add up to 10, so it's not a multiple of 3. It's not a multiple of 5. 12 minus 14 is minus 2. It's not a multiple of 7. 1 subtract 2 plus 7. It's not a multiple. In fact, that's the one we did earlier on. It was prime. 127 is a prime number. So we went quite a long way between prime numbers. We've got a gap of 14 from that prime number to the next prime number. And you can see why the gaps are going to increase. Because when you have a number like, 1017, you've got to check a lot of numbers to see if they're prime beforehand. The number I gave you, 1017, that's the digits add up to 9. So we know that's not prime. But then what happens when you get to 1019? You've got to check a lot of numbers before you can check to see if it's prime. And so as you get over 1,000, you get prime gaps of, quite quickly you get prime gaps of bigger than 14, 22 and 34. You get quite big prime gaps. So the larger the numbers that get, the less prime numbers you get, although it fluctuates. The gaps go up and down and up and down. I want to give you an idea of mathematical thinking now. And if you can understand this, it's a complicated concept. But if you can understand this concept, you're well on your way to becoming a mathematician. So, at some point, somebody posed the idea, surely eventually we will get to the last prime number. Surely eventually, we're going to get to such large numbers that there'll be no more prime numbers. And there was a famous answer to that question. And I'm sort of introducing you to the answer to that question. And to introduce you to that answer, I need to simplify things a little bit. So I'm going to start off with an imagination game, something where we're going to imagine something's true that isn't true. So I'm going to imagine that the last prime number is 23. Now, imagination games are a real test of your intelligence, because only humans can play make-believe, play this idea. Well, that's not true that only humans can do it. I think some apes can do it, and I think maybe even dolphins can do it, but there aren't many creatures that can do this idea of imagining something's true that's not true. Imagine the last prime number is 23. So, well, we know that 29 is prime, so that's nonsense. So, but just take it for granted that 23 is the last prime number. Take all of the prime numbers that we think exist. So remember, 23 is our last prime number. So the prime numbers we've got are 2, 3, 5, 7, 9 isn't prime, 11, 13, 15 isn't prime, 17, 19, 21 isn't prime, and 23. Multiply them all together. So I'm going to multiply them all together. 2 times 3 times 5 times 7 times 11 times 13 times 17 times 19 times 23, and then I'm going to add 1 to that. And so the answer that I've got is 223,092,871. It's a huge number, obviously, because we multiplied so many numbers together to get it. And I'm not asking you the question, is this a prime number? That's not the question I'm asking you. That is not the question I'm asking you. I'm asking you, do any of the prime numbers that we believe exist in our imagination game, do any of these prime numbers go into that? And you can answer that without a calculator, just by using your thought processes. Just by using, you don't need to do any working out at all. Just by using your thought process. Are any of these numbers, is 2 a factor of that? Is 3 a factor of that? You don't need to do the sum of the digits to test to see if 3 is a factor of that. Is 5 a factor of that? I'll give you a clue, for instance, about the 3 one. If I didn't add the 1 on there and that ended in an 870, I bet you the sum of the digits would be a multiple of 3. And then obviously by adding the 1 on there, that's going to stop the sum of the digits being a multiple of 3. Okay, that's the last question I want to pose before I end this lesson. And the homework, I'm not going to give it to you right now. I'll give it to you after the lesson because I want to go through some of this in a bit more detail and see exactly how well you cope with all of that. Okay, so that's it. That's the end of our lesson precursor. I will see you in the lesson. Bye.